All right, so in terms of what we're going to talk about in these lessons, I just want us to go over linearization. So just a quick review on what we did last class, right? So we kind of ended off with Taylor form of a line. Right, so Taylor form, once again, is my preferred way of writing linear functions. So Taylor form of a line gives us a tangent line at some point. And the notation that I used for the point that we cared about was f of a. Once again, just x and f of x. So Taylor form, which I was going t of x, just a number one, represent Taylor form. Number two, just kind of show that it was like a tangent line, was we had f of a, the y coordinate. Then we added on f prime of a, which we remember is the slope of the line when x is equal to a, times x minus a. So why do we care about this Taylor form of a line? Well, it helps us when we have to do what's called linearization, which is just a fancy name for making predictions of y values. So suppose I had some function, right? So here's my function f of x. And so I got some function right there. And the idea here is that if I have this function, well, maybe there are 2 points that are on this graph. The key thing is that there's some easy to find point. That's what this a f of a is going to represent. So just as an example, if I had just some function like um, e to the x, say, f of 0 equals e to the 0, which is 1, that's a really easy point to find, right? We could just do it in our heads, basically. We'd have a lot more difficulty if I said, well, find me f of 0.6391, right? So e to the 0.6931, we'd have to go, I didn't even write the number right. That's how hard it was. 6391, right? We would have to actually go to a calculator, get some approximations, right? That would be much harder to find. So this first point is the easy one that's going to be, the kind of our base point. And then suppose there's some other point on the line that's maybe a harder point. This is a hard point to find. So the idea of linearization is we can say, well, so long as my function is differentiable, I can take the derivative in some interval. Well, I could create a tangent line that hits the point at that nice, easy point right there. Well, since I have some line that hits at just that point, we could say write Taylor's form of the line. So I know that, once again, this is my easy point, that I could find, say, the slope at a f of a. It's simply going to be f prime of a. And then there's some point way out in the future here. So if I don't even worry about that point for a second, just the equation of Taylor's form would be, I'll just call it for now, say t of x, once again, it's the same thing, equals f of a plus f prime of a times x minus a, right? So that's Taylor form of a line. But here's kind of the connection that we want to make for linearization. Well, since I have this line, there's going to be some points on that line that has the same x coordinate as this really tough to find point on our function. Right, so those 2 points have the same value of x. So long as like a couple of things are going to happen that we're going to care about a little bit later, so long as those things happen, this value L of x is a pretty good approximation for that value f of x. So L of x is our approximation for the value f of x. So if I just looked at these equations, again, we kind of can see where Taylor's form might help us out here. This difference between a and x, right there, is simply x minus a. So if I start at a f of a and I just go over x minus a, I'm going to go up f prime of a because that's what our slope is. We're going to end up with this form right here. So I guess I technically should have written this right down there. So this is what we call the linearization. Again, linearization is just Taylor form of a line. The only difference is that when we say linearization, it means we're trying to figure out some y value based off of some easy to find x value in our function. So here's our linearization formula. So f prime of x, right? That's our approximate, or sorry, that's our exact y value on the function is approximately equal to L of x, that is the y value on our line with the same x coordinate as f of x. And that linearization, that L of x, is once again simply Taylor's form of a line. Right, so we can, this is kind of like the in your own words kind of part. So all of this is simply Taylor form of a line. All right, so again, the takeaway here, I'm going to do an example in the next video, so these videos aren't like massively long. So the takeaway here is that if we want to find some hard to find value, we can approximate that value with some other y value that's lined up with the same on the same x. And to find that approximate value, we could do it by knowing some easy to find value on our function. That's going to be the takeaway that we're going to do in the next question.